Yeah, so hello all. Good evening. So this is our week 8. I'm Jagriti, TA for the course of Data Analytics with Python. I'm a PMRA fellow at IIT Gandhinagar. I'm a third year PhD student. I work in the discipline of biological sciences and engineering, and my work research is related to medical ultrasound. I'm trying to differentiate in between types of tissues. I'm trying to characterize different types of tissues using quantitative ultrasound techniques. So I would just need to know first from all of you that is my other device visible, because I can't see on my second screen that if my first device is visible or not. So is my screen visible to all of you?
Yes, ma'am.
Okay, so probably I don't have any feedback from my second device now. Let me try sharing with this one and then I'll try sharing with the other one. Share. Stop sharing. Okay, my screen is visible, right?
Yes, ma'am.
Okay. There might be any issues today. Anyways, so we'll start from categorical variable regression. So last week, this was the one that was left. So for now, we were looking at that the variables that we were studying, the independent and dependent variables, they were all continuous. That's why we were able to do the regression analysis there. We didn't have any such variable which was like, let's say, was logically defined. Let's say if either the condition is true or false, or it's 0 or 1, something like that. Or we didn't had something that, okay, I have a certain group, let's differentiate this to groups as like this. So as in schools, we previously had something like we had different divisions, right? So based on this different divisions, we were doing things like, okay, people in A class, people in B class, things like that. Okay, so this categorical variable regression will now help us do the regression analysis with respect to a particular variable that we're looking at. Okay. So this agenda for this lecture was, we'll see that how to handle these variables while doing the regression analysis, to illustrate the use and interpretation of these variables, and a demo on Python for the same. Okay, so then we'll see that what are the dummy variables. So here what we do is like we'll introduce one variable as a dummy variable and then assign it to the categorical variable. Okay, so something just happened in my screen. I don't know what happened. Okay. Anyways, uh, yeah. So what are these dummy variables? The dummy variables are nothing but these are indicator variables which allow us to include the categorical variable, which can be this gender or let's say division of classes, something like that in the regression models. So a dummy variable can only take two values. That is, similarly, we can do it as logical values. It can be 0 if something is not there, and can be 1 if the category is present there. Okay. So there was one such example given over here, and in this particular example, there was a question or problem was the repair time. Now, this repair time in ours is that dependent variable that we're looking at, and this dependent variable is dependent on these two independent variables. One is the number of months since the last maintenance service, and next is the type of the problem, whether it's mechanical or electrical. So in our case, we can say that one is 0 and one is 1. So we have two variables here. Okay. So based on the number of levels, we will define the dummy variables also. So if levels are, say, let's say x, then the dummy variables would be n minus 1. If the dummy variables are, let's say, some x, then the number of levels would be n minus 1, something like that. Okay. So here then they divided, okay, this is our service call, this is my last month, this is my type of service, and the repair time in hours, how many hours that I have. So what we did is like, okay, let's see and just read the table in here. So same all libraries that we have seen till now, we need pandas, we need matplotlib, we need that stat models to do regression and all those analysis, or even OLS also. Then we'll import the linear regression that we learned in last class. Then we have stats, we have Seaborn library for the OLS only, probably, I guess, yeah, for the least squares. Then we have NumPy, we have Matplotlib, that is for plotting, and then we have the stats model. Now, so you read the table, you see all the libraries in this way. Sorry, you see the table in that way. You read the table. Now you want to see the linear regression. Let's just do a scatter plot here. It's not linear regression yet. We are just plotting the data. So what do you see? The data is very much scattered here and there, and you can't form a particular line across it. So even if you make a line, something like this, the red line that is given over here, you don't see a specific trend. It's like all points are something like this. They are scattered around the plane. So you won't be able to see that it is actually linearly related or not. Okay. So then what do? Like we just take the summary out from that table, and this was our independent variable. So we gave it that as a constant, and we did the regular regression fitting that we were doing like till now. So this is how this part of regression dot fit here, this thing. Okay, now when this is done, we know that what all things we need to is like read from this table. We know we'll see the R square, we see the adjacent R square, we see the F statistic, the probability of F statistic. Till now we won't go into others. We know the degree of freedom for the model. We had two different variables, that would be one, right? Now for the things that we know till now is the coefficient and the standard error. So if you want to find a regression equation, that regression equation would be something like this particular variable, our intercept, plus x times our slope of the variable, that is the independent variable. Okay. So, and then we can also see the probability against the same true. So this is how our linear regression equation was like. Now we don't know this error term yet, because, and then what was the another assumption, that the error in linear regression or regression should follow which trend, or it should be what? Yeah, so the error in linear regression should be normally distributed. Okay. So this should be normally distributed. The slides are visible to you all, right?
Yes, ma'am.
Thanks. So then what we'll do is, like, in order to see if our data is normally distributed or not, we'll just make a QQ plot that we saw last time. So this QQ plot is nothing but prop.plot, and you add a QQ plot to it. So now you plot the QQ plot, you see, okay, the data is somewhat like this. So it is somehow is like it's based on the plot line that we are looking at. So we can say, so perhaps, that the residuals or the errors that we are looking over here is normally distributed or not. So we see that, okay, somewhat it's aligning to, and it can or cannot be. So what do we do is, like, we'll make some dummies here. That is the variables that we have. So the function for the same is this one, that is get dummies. PD dot get dummies. As simple as that. So you need to add some dummies. The function is PD dot get dummies. That dummy would be a type of repair, which was like electrical and mechanical. So you add this. Yeah, yes.
Can you please explain the dummy variable once more?
Sorry.
Can you please explain the dummy variable once more?
Yeah, yes. So this dummy variable we are adding, so we just start. We are adding this dummy variable to define a categorical variable. So that categorical variable would be a representative of this dummy variable. So we are doing nothing but, okay, we'll just add the type of repair. Our type of repair, at first what it started was using this thing. Now here it is either electrical or mechanical. So we'll assign this electrical and mechanical as two variables there, like that. And then these are the dummy variables that we get in our model. Now what we'll do is, like, we'll just print those dummies. Now when we want to do our this regression analysis, here what we did, the summary model, when we want to do this regression fitting, we'll take one variable, or we'll drop either one variable, and we'll do the analysis for that, which will help us know our data more it's like will help us analyze our data in a way that either it's like how it is falling for the electrical repairs, how it's falling for the mechanical repair. Because analyzing both of them together does not just make any sense, that okay, you're looking for electrical and mechanical together. Let's just look both of them separately and do their analysis separately. So those are the dummy variables that we have defined here. Okay, so we define the dummy variables. Now what we do is, like, here they say that 0 is for mechanical and 1 is for electrical. So wherever you see 1, that is your electrical. Wherever you see 0, that is your mechanical variable. Okay, so then we add the variables to the table. So this is just to add something new, a variable to some the table that we have, or you can also say some constant string values. So here they have termed it as dummies. So that is how they add it. So that is get underscore dummies to the table, that is nothing but type of repair. So now we have successfully added this type of repair to our table, that is 0101 electrical or mechanical. Now what we'll do is like we'll drop one of the variables. So let's say we drop this mechanical one. Now, when we drop the mechanical one, all of our analysis that we are doing would only involve the effect due to the electrical repairs. Okay, so we have concatenated the table with the just dummies and we just drop it, dot drop from the type of repair. You drop the mechanical one. In place is true, axis is 1, along which axis, the column 1 that we're looking at. Then you make a summary table. Now your constants would be two other constants. One is the independent variable that you had, the months per last service. Another would be your electrical effect, the electrical repair against which you want to see the effect of your regression. You fit it, you find the summary. Now what you see is like you again make your regression equation. Now this regression equation would be this constant plus this value times this plus this value times this electrical repair. Now, at first, when we didn't had these variables and we just did everything for the data set, if you notice the R square is 0.534 and here it's also 0.476. Now, when we just do it separately for each and every category, what we see here that the R square improved. That means independently the variables or the data is making some sense. It's like we're able to interpret it in a way. Whereas if we take both of them together, there's just no alignment in between the data. So what we see now, the R square has been improved and then we see that, okay, the data is well properly fitting, regression analysis is being done over there. Again, the probability if you see is also very less than 0.05. So we say that yes, it is significantly or not even significantly that our data is linearly related. Okay, so what we had, if the type of repair was mechanical, it was 0. If it was electrical, it was 1. Then you define your entire equation over here. Now this equations here we have, but we still don't have this error term here. So we'll find the error term later, but for regression analysis, we don't need it for now. Then if it's mechanical, you add it 0. If it's electrical, you add it 1. 1 and the other would be 1 minus the other thing. Same as probability and probability of failure and probability of successes. Okay. So then how do you interpret these parameters as? Now both of these parameters will have a similar slope because eventually you're looking at the same data set, but you are ignoring some variables, you are ignoring the other variables. So their slope would remain the same, but only the intercept from which a particular point is starting from or where it is leading to, only that particular intercept will end differ in your equation. So hence it's like if your intercept is beta naught in equation 1 for mechanical, it would be beta naught plus beta 2 for another equation variable. So these are nothing but your regression coefficients what you have. Okay, so those things would only be you'll able to do when you directly do or compute the variables. Then when you interpret this, this is nothing but a difference in between the mean time repair for electrical and mean time repair for mechanical. How so? Here you see it's beta naught, here you see beta naught plus beta 2. Difference in between both of them would be nothing but beta 2. Okay. So beta 2 is the repair. Now if one is positive, then with respect to what you're looking at, that would be at higher value, another would be at lower value. If it's negative, the lower one would be at higher value and the upper one would be at lower value. Okay, so if it's positive, then we see that the repair of electrical would be greater than for the mechanical because here at first we started from the electrical repairs. And if it's negative, then we see that for electrical, it is less than that of the mechanical repairs. Okay, it's well understood over here. Now finally, if it's 0, then we say that yes, there are no differences in between the electrical and mechanical repair, and the type of repair is not even related to the repair time. If either it's mechanical repair or it's electrical repair. Okay, so till now this part is clear. How do we add a variable? How do we interpret it? How do we see the difference of the effects in between them? And if the difference is higher or lower, how do we interpret our results accordingly? This is clear till now? Okay, so I guess See, all of you understand? It's okay. So when we do interpreter analysis, we see that the value came out to be positive. So we know that, okay, electrical repairs will require some X amount of time longer than that of the mechanical repairs. Where it is like in, say, for in real time situation, even if you see electrical repairs have given the situation of repair or given the order of repair, you see that, okay, it might take some time. They might not have certain variables. And mechanical repairs is like you just take the things out here and there and you look for them. If the work is not too long, it might be done before time. Whereas electrical, in some cases, it matters. So based on the situation or based on the problem that you're facing, something like that. Okay, so then how to interpret it? So you make some plots, regression plots against both of them. You add the slope of lines. Now you see for electrical, these were your variables. So now it's following properly your plots here also. For mechanical, all of them like this. So it's also linearly related to it. How do you interpret your parameters if it's affected by the other constant variable that you are thinking if it would be? And if it is, and if the question has given to us, then you better add that another variable as a dummy variable. You do the analysis against that particular dummy variable. Okay. So now let's say here we only have two categorical variables. What if they are more than that? What if you need to do an analysis that is like say for 5 or 10 variables? In such cases, if your variable has some n number of levels, then how many number of variables should you model? You'll model like k minus 1 dummy variables. So here we have like 2, right? And then we modeled it for 1. So that was like we only we only saw the effect for an electrical one. Accordingly, we knew the effect for mechanical one. Now it's for n number of times, you'll do the effect for n minus 1 times. Okay. So the care must be taken in defining and interpreting the dummy variables. Okay. So there's another such problem. The problem was like for with number of average salary sales and in between male and female. So here we have like 2 and the analysis will do it was like only once, either for male or female. So this is a gender that is given to us. Now we add this gender, we just read the table, we plot it. Now you see it's pretty much linearly regulated, but there might be something that's influencing the effect of salary. So we just did it for everything. Now our R square is pretty much higher. So in such cases, we don't actually need to go further. But if we want to, and if we want to see the difference in between the measurements. So what we had previously, we also saw that, okay, this is our actual observed data. And when we do linear regression, we fit it with a model. Now the difference in between both of them is called an error, a residual, or a bias, something like that. Okay. So here, if you just get an influence and from the influence, you plot the residual is like the standardized residual that we saw. Now this residual is something like this. So the plots are like this. Now at 0, if you see, the error is not even minimizing to a point. So we are not able to see that the values are getting minimized, the variability getting lesser. So there is an effect due to males and females. In such cases where you get some results where R square is pretty much higher, then you need to understand that why is it that higher and how come if the residual are also lesser or higher than it. Okay. So then you just do is like you'll find the residuals of the plot, you just directly do the QQ plot. So here if you see in the QQ plot, there's also some variability from the linearly related data. So that means that yes, there is some issue due to the data or your data set is not following a normality distribution, right? It's not normal. So what you do, you again add a dummy variable. One is for female, one is for males and females. Let's say males got a 0, females got a 1. Now you drop one of the variable, you add the variable dummy variable to your data set. You drop one of them. Let's say I dropped males here. So I just see the effect due to females. And then I see that, okay, R square has been lessened to a point. Even it is negative in some cases and my probability is also higher. What that means is that for female, our data set is not linearly related. Okay, so we can't do linear regression on it. So we see that the intercept was some value is the average salary for male as we coded this for males and this for this. Value of the slope will tell us that the salary is less than that of this particular value. So we just did the analysis for one variable. You can do the analysis for the another variable and you can see the effect accordingly. This constant might vary, but your conclusion would remain the same. So you'll have to see that. Okay, that is how we saw that the slope will remain the same. Only the intercept would change. The intercept can be positive or negative. So your conclusion will also change with respect to it. Okay, now they did against males. So with respect to males, what you see, the value increased. It increased there also, and the probability decreased here also. That means that yes is like it increased. So what would have happened if we had used like 0 for females and 1 for males in our data? Would our results be any different? What if we change the order of them? Okay, so now what I did, I just dropped my female thing. Now female I dropped and I saw the value is almost the same. So not much change here till now. So now our case is like male as 1 and female as 0. So not really. With coding as above, we saw that the intercept would change to some value. The slope would still be this point. So even if you change the order of your categorical variables, the slope would always remain the same. The intercept will only change in those cases. Okay. But now it would have a positive sign reflecting that average male salary is higher than the average female salary. So only your conclusion accordingly will change, or the inference that you are taking from the data will change. Okay. So predicted salaries would not change no matter how the dummy variable is quoted there. So nx, what you find, the predicted things won't change with respect to if you change the dummy variables or the order of the dummy variables. Okay. Then some more on it. So we just see that number of dummy variables is equals to number of levels minus 1. Okay. And then this is with respect to the job grade. So again, you find the number of dummy variables in such case. So this is like job 3 is the reference category. So since job 3 is the reference category, they took it in, let's say binary numbers. So 0, 0, 0, 1 and 1, 0. 1 and 2 variable that you have. Okay. Add it in a data file for job 1 and 2 grades. And then again do the similar analysis there. Okay. So is dummy variable is clear? Sorry, not dummy variable. Doing regression and with the categorical data, it's clear till now? Okay. So what I'll do very quickly, I'll just log out from this session and I'll rejoin here because I don't actually get a feedback. What am I teaching and what I can see, but my other device is still in the meeting. Okay, so just give me 2-3 minutes. I'll see if I can do something. Be Yes, so now I see my screen, the screen. Okay, thanks for waiting over here. Now we'll go to the regression. Sorry, what's happening to it today? We'll go towards the maximum likelihood estimation. Okay, so this is the part that I like, but we won't do logistic regression today because these things are something that you should take some time to digest. In the assignment also, there's not much on it, so let's just take it on some chunks of it so that you remember how these things are done. And these are the things if probably if you guys are in, let's say, doing some simulation work or numerically solving some equations and partial and all, or you're doing something as stats, you might require these things to be done. So let's take it one by one. You first go through it them by today, implement it by yourselves, see the data, see your distributions, do it for a number of distributions, and then in the next week we'll do for logistic regression and we'll compare the linear and the logistic ones. Okay. So this is a term called as maximum likelihood estimation. So maximum, we are let's split it into some keywords. Okay. So first keyword is maximum. Next keyword is likelihood. And the third keyword over here is estimation. Okay. Now here, first thing what you have is your likelihood function. Okay. Now when you have your likelihood function, this is your likelihood function. It's going somewhere else. Okay, let's remove it. Okay. First, what you have is your, let's take this, is your likelihood function. After the likelihood function, what you do is like you maximize the likelihood function. And from both of them, you estimate a value for that particular function for a sample value that you're looking at. Okay. So this is how the trend goes. You first see a likelihood, you make a likelihood function, you maximize that likelihood function, and then you estimate the value of that maximum likelihood for a particular sample value that you're looking at. So that is how it gives you an estimate. So this is how it's like maximum likelihood estimator. So our agenda is just to see the theory behind it, and we'll just do some examples. Examples as is, we'll derive it for distributions that are known. Okay. So this was introduced by this R.A. Fisher in early 1920s. So what is being done over here? So this is the actual definition of it. What we do is like we'll find the most likely density function, the likeliest density function that would have generated the data. It requires to make, so first it requires us to make an assumption about the data in a way that if you see here, these are your data points, right? So these are n number of your data points. Now, which particular type of distribution would fit? Would this fit, or this one fit? So from this, looking at it, we see that, oh, what happened? Oh, the side dot skipped. So if you see over here, this is not fitting because it's removing all the other points. If you see this one, this is removing this point, but it is actually fitting all of the other points. So either the blue one or either the red one, because it's like spreaded all over the entire area, can be used to fit your particular model. So both, all of them are normally distributed data set, but which particular model it is fitting to, which particular model has a maximum fit with respect to our determined data, that we need to look over there. Okay, so this is an example one such. Now we learned about the categorical and the dummy variables. So for now, the example states that there is like someone made some n number of bike helmets, and within those bike helmets, some are flawed and some are not, right? So we first took the probability of the flawed helmets, and then we took the proportion of all the helmets that are flawed, right? So we know Bernoulli's theorem. We have a probability of success and a probability of failure. So let's say x1 is this first one is flawed, and so the probability, let's say probability not, the variable that we are assigning to it is 1. If it's not, it would be 0. So this is actually taken from this particular group book. If you want to look at, you can look at that book. It's also very good. This book has some examples around probability and statistics, not directly related to what would be there in the exam, but yes, would enhance your understanding. Definitely it would enhance. And then let's say if the 10th helmet is flawed or not, the variables are also given accordingly, right? So then what we do is like we'll obtain it for a sample. Let's say for this first 1, 3, and 10, the helmets were flawed. So we gave it as 1, the others weren't, so those were like zeros. So we know from Bernoulli's, we know this like P and 1 minus P power 1 by 1 minus X. So this is your probability of success, this is your probability of failure. It is done for n number of times, that's why this Xi over here and 1 minus Xi over here. Now we suppose that all of the helmets are independent from each other. So what we do is like there would be, if they are independent, their joint probability mass function is nothing but their product of the individual PMF. So those would be multiplied. Okay, so in this way, it's like for x1, x2, n3, n3. So this is a joint PMF. We'll just multiply n number of helmets that we have likely. So if first one is P, next 7 would be, so okay, let's say first is our Pth one, next is 1 minus P, next again is P, 1 minus P, then we have a P, then 1 minus P. So we have like, let's say we started from 0, sorry, so 0 to 9. Okay, something like this. So 0, 1, 2, 3, 4, 5, and this still the 10 number of variables. So ninth variable. So what we see is like for 3, we know that it is flawed. So for them, our probability is like P. And for the other ones, I don't know what happened. And for the other ones here, our probability is it isn't flawed. Okay, something like this. It's not coming on the screen or something. 2 minutes, huh? Oh, my other session is trying to reconnect. Okay. Green is not yet coming. Okay. Ayo. Yeah, I guess there's some network issues. Okay. So then this isn't flawed. Okay. So let's say our probability, if it is flawed, it's something like this. And the other probabilities would be 1 minus that variable. So we got something like this. Now let's say if our value is like 0.5. So 0.5 for flawing, 1 for it's if it's not flawed. So we get something like this. So now you see like now the probability is getting increased. Now here the value was that, so that the probability got increased. So the significance level to which our values are different got also increased in a way it's now more significantly related. Okay, not increased that okay it's reaching 0.05 and it is now no more related. It's something similar to how you say that okay increase the temperature of the air conditioner where you essentially wanted it to be cooler, but you see that increase it, not but not saying that okay you decrease it, something like that. Okay, so things that are is like mean the same but has some different meaning, something like that. It's like if you hear it similarly, so, and you it's like the output is something different from them, something like that. So then now it asks us that from what particular value of p is the obtained sample most likely to have occurred. Is like if it maximizes the value that we want, and that is for what value in this particular equation of joint PMF, what value of p and how much larger it can be. So how do we determine for it? So we have something as likelihood function. So what we did is like we plotted a function for n number of p values. So we did it for this 10 number of p values, right? Wait. Yeah. So we did it for 10 p is like this p is equals to 1 0 1 2 0 to 1. We plotted it in the intervals of 0 0.5 0 0.2, so that those are like 5 values that we have over 6 5 6 values that we have over here. And then we plotted the likelihood. So what you see in this likelihood, we see that after 0.3 you have some maximum value. Let's say for 0.4 we got a maximum value over here. So it is peaking above 0.3 and the proportion of all flawed helmets in the sample. So something similar to this 3 or these two ranges, we might get a maximum value where our predicted data and where our observed data are both closely linked to each other. Okay, then what we do is like you just plot a natural logarithmic. So here the scale is linear. Okay. Now what you do, you plot it in a log scale here. So you plot it in a log 10 or a natural log scale. Here what they have done is they have taken a natural log of it. So natural log of our likelihood scale. Okay, so natural log of likelihood scale they have plotted. So what you see over here, it is increasing and then again it's decreasing. So what you see, if this particular function right here, it's increasing strictly for a certain number of time, this is also doing some similarly. After that, it is starting to decrease. It is also starting to decrease over here. So what do you see? Let's say if we assume that at this particular function, it's strictly increasing function of g of u, then ln n will also be a strictly function that is increasing. So we'll need to find u that is maximum for the function of g of u that will also be similar to that particular function, right? So what we mean is that u would be maximum for a function that is g of u, right? And then u would be maximum for a function that is ln of g of u. Okay, where u is actually a function of g. So we see that this will give us the maximum value that we get in this is also the maximum value that we get in this particular term. Okay. So how do we do that? So we verified that by using calculus, the value of p that maximizes the equation we saw here previously, and then we'll work around with this particular natural log and we'll see how it comes through. So here they have just taken logarithm and then differentiated it. So here what they do is like now you have this is what it is your likelihood function, right? So this is your likelihood function. If someone can say what is x1 to x10 and what is p here? Here. So x1 to x10 are our sample data or observed data. And this is our probability that we are looking at. Okay. And then we take this thing. So this thing p raised to p cube and 1 minus p raised to 7, from where did it come? Here. This term that we had. Okay. So this is your probability. So this is your likelihood function that you get. You take the log of the likelihood function. So how do you take log of it? You now this a and b would nothing but, I hope you all know this part. This would be log of a plus log of b. Right? Now log of this term would be nothing but you're taking log of this term with respect to x, but x you don't have, so you're just taking a log of the function. Just taking log of the function would be nothing but 3 ln p if you have a power, and it would be 7 ln 1 minus p. Okay, you took this term. Now what you do is like you differentiate it. Differentiation would give you 3 by p, 7 by 1 minus p, and for p you again do it, so that would be minus 1. Okay. So what you have is like 3 by p minus of 7 by 1 minus p. Now what you do, you you equate this term to 0. So have they given that? I don't know. Equate this term to 0, you get 3 by p is equals to 7 by 1 minus p. So 3 minus 3p is equals to 7p. 3 is equals to 10p. So your p is equals to 3 by 10. The probability that you get for this binomial distribution is 0.3. Okay, so what you get over here, oh yeah, yes, they've done. So you equate the derivative to 0. Why did we did the derivative to 0? If you remember, when we wanted to find the global maxima or minima and the local maxima or minima, first we differentiated our equation, made it equals to 0, found the zeros formed the same. Then we did the partial derivative, it's like squared derivative of it, and then we saw that the second order derivative, we saw that if it was less than or if it was greater than 0, then our value was like accordingly a maxima or a minima that we wanted. So now here we are just wanting to see if it's giving us a value or not, or if it's maximum or minimum. So our point estimate here is p equals to 0.3. So that is the probability of getting a helmet that is flawed. Okay, so this will maximize our likelihood function for the observed sample. In that case, again, if you want to do a final state ensure to make sure it, then you do a second derivative to make sure that the maxima has been obtained, right? But since we saw from this particular figure that after this particular value it is decreasing, and after this particular value it is also decreasing, so we are now pretty sure that okay, at 0.3 it would be. But in exam, if you want to confirm, just do a second order derivative of it. It will give you a direct answer, which would essentially be the same. But for that you need to first plot the data, so better be safe and do the second order derivative and see the replies. Okay, now so we were told that suppose that rather being told that the condition of every helmet had been informed that 3 of 10 were flawed. So what we do is like we'll do normal combination. So we'll do 10cx, we'll do probability of the flawed one, we'll do the probability of which are not flawed. So 10 minus x, for x equals to 3, this equation will become something like this. The binomial coefficient will come as 0.3. So this is as simple as what we had from previous terms. Now, how do we actually do maximum likelihood? Okay, so be with me till this part. It's not that much. In I guess probably 4-5 slides. In the next one, again 4-5 slides, then we'll be done. But you need to understand this at a level detail. Okay, so now let's say if this particular sample data has a joint PMF or a PDF, let's say we determine that function or PDF, we say it as f of x1, x2, x3, n3, and these are some terms that we have, right? Now let's say these all parameters have some unknown values. What are these? These are the values where which the function will be maximized to the observed data that we are getting against these values. Okay. Now these are our observed data sample. So sample values. So these are the sample values. These are some unknown values that we don't know and we don't even want to know for now. So this particular function, we call it as likelihood function. Okay. Now what we do is like, we'll take the estimates of this particular function. So we maximize this function, right? So the maximum likelihood estimate, MLE, for this particular function is when you find the theta 1, theta till theta m, for this particular terms, you get something as theta 1 cap. And these are the values for the ith that maximize the maximum likelihood function. So eventually what you do is like you find this value for a maximum of this value, you input this value to this xith term, and you estimate the theta cap for them. Okay. So these are like one after another. When we do a sum, you'll be able to know. So basically, simply it's nothing but it will just tell you how likely your observed sample is a function of the possible parameter value and how finely it agrees most closely with your observed data. So the parameter values that you are computing, or you'll get the possible parameter values, the estimates, how likely they are close to the observed data points that you have with you. Now from that also you can determine a distribution from your data, or from the distribution you can determine the type of the data, right? So we'll just see and derive it for the Poisson's distribution. Okay, so Poisson's distribution, all of you know that it is like e raised to minus mu, mu raised to x, mu is our mean, by x factorial, right? So this is if done for n number of variables, then how will we write as like x1 here, x2 till n number of times. Then what we do, so this is all nothing but a product of all of them. So we have this as a sign of sum and this as a sign of product. Okay. So we do the product from I is like I equals to n, I to 1 to n number of points, e raised to minus mu, mu is like mean would remain the same, and mu raised to xi. So xi number of terms we have to repeat it. And then we do e raised to minus mu. So n times, if let's say if n is our last index, e raised to minus mu and mu raised to x times x bar, nx bar. Nx bar, why? Because this is our sum mean. So that would be nx bar. Now, can someone say that where did this term went? It's like when I was looking at the slides at first, for me it was, oh, factorial term got disappeared. Where? Why? When I went to the second slide, it was well obvious for me. If you have seen, or if you also have a similar doubt to me, say it loud. No doubts. Yeah, so this factorial term, okay, so let's see. What is the factorial of 1? 1. For 2, it's 2. For 3, it's 6. For 4, times 4. Okay. So this factorial function got removed because it was a constant. Constants won't affect your maximum likelihood function. Functions would only be affected by the estimates of the function. Those estimates come with respect to the dependent and the independent variable that you have in your equation. Okay, so these are just a constant. They do not influence the relative likelihood of differences values in the parameter. So usually we work with the log likelihood rather than the likelihood, because solving log likelihood essentially is like taking the derivative of log likelihood and then maximizing it. It's pretty easy with respect to the likelihood function itself. That's why we directly do using the log likelihood function. So what we do is like e raised to n mu, mu raised to nx bar. You take the log of it. So this would be a minus mu ln e. So that would be minus mu. The exponential will come directly outside. This will also come. You have log mu. So what you do now with respect to the mean, you take the derivative. So this would be mu. Oh, sorry, mu you take it. So this would be minus n. This would be n x bar divided by mu. Okay. So then you get that this particular values are same. So what you get is your population mean is equals to your sample mean, which is nothing but your moment estimator, right? So this is how we computed it for a estimator value. So in this case, our MLE is same as that of the moment estimator. So what we did, the maximum likelihood function that we got is similar to that of the moment estimator that we have. Okay. Let's say we did it for another parameter. So this is for the exponential distribution. Okay. So for the exponential distribution, what we do is like we have the term as lambda e raised to minus lambda x. So you do it for n number of times, you assume that it is independent. So, or the likelihood for all of the functions is if it's independent, then what we'll do is like we'll take a product of the individual PMFs of them. So the natural likelihood of them would become nothing but you take log of ln of natural ln of this term. So that is nothing but here as it said. So you take a plus, so this is a, this is b, you take a plus b, and then that would be ln lambda, and then this would be minus lambda xi. Okay, it would be like this, something like this. Now what you do is like you differentiate this term. When differentiating, you get n by lambda minus this would be only xi. Now you equate it to 0, you get lambda, you get something as n by lambda is equals to summation of xi, and lambda is equals to n by summation xi. Now this is something that we have seen previously, but what we have seen is summation of xi by n. So this is that 1 by x bar. So for the exponential distribution, the mean is equals to the inverse of the sample mean that we have. Okay, so this is how we computed the moments of estimator, the moments for the maximum likelihood estimator. Okay. Now, if it's a normal distribution that we all of you have been known till now and how the distribution comes, and it's also is like a very big family of distributions. Any distribution that you want to model, it would it's like it would have some branch or it would be related with the normal distribution. So in a way, if you don't have any particular data, you don't know which particular distribution your data follows, goes with the normal distribution, and then from it categorically try and see which particular distribution is appropriate for your own data set. Okay, so definition for the same is 1 by 2 pi sigma square e raised to minus x by mu divided by 2 sigma square. So you take log of it because it's for any number of variables. So this is how your definition is. So you take minus n by 2. Oh, sorry, this would be n by 2 and this is y 1 by 2 sigma square. So what you are doing over here, you're taking log of the entire thing. You're not yet differentiating it. Okay, so remember that term in hand. So why it became like this is because no comments. So this is something we can write it as 2 pi sigma square minus 1 times n by 2. So that is why the minus sign came here. We have n by 2 and we have log of 2 sigma square. Okay, exponential came all out. You have the inside term. Minus this term also, ln ln would be cancelled here and you get this entire term. No need to do anything over here, right? So xi by this by 2 sigma square, all the same things. Now what you do is like you'll differentiate this term, you'll do partial differentiation because now you have two different variables here with respect to mu, and you do the differentiation with respect to sigma square. Now when you're trying to do it for sigma square, try differentiating x as sigma square so that this is equals to something like this, and then you do it the differentiation. If you don't know, it's like if you're not able to do directly in terms of sigma square, and in the end to directly differentiate it, what you'll essentially get is these parameters. You will get that the moment estimator and the sample mean are same. You'll also get that the variance is equals to xi minus x bar divided whole square by n. So same thing what standard deviation comes to. So standard deviation is usually equals to square root of the deviation of a particular sample from the sample mean divided by this n. Something like this is our what do you say, our standard deviation. When you square all of those, you get something like this. Sorry, this is not it. This is like this by square root of n. So that's something similar to your standard error. Okay. So this is how you estimate it for these parameters. Any doubts when we did for Poisson's distribution, for exponential distribution, for normal distribution? So here you can just solve for these two equations. When you solve, compare these two parameters, you'll be able to get. I did it myself, I was able to getting. So if you also do from equation 2, you'll get this particular value. From equation 1, you'll get this particular value. Any questions? If not, there's also only one small example now, and then we'll go towards the assignment then. So most of the time, this MLEs, they are something like you won't be able to solve them by your hand, and then you'll need something as Python or MATLAB to compute it for you. So you'll have to compute it, let's say you'll have to iterate it for n number of variables. You can't just always take ln of it and solve it. So you have tools like Mathematica, you have MATLAB, you have Python, where you can numerically solve these equations. You can derive their differentiation, you can maximize them, you can minimize the error, all those things you can do there. So instead, if at some time, if the calculations get too complex, then you can use these tools in order to make your computations or make your solvings easier. Okay. Now we just want to see some and make an understanding or find the intuition behind the MLE and this. There's also one more thing below. So using theory and examples, right? So we'll be seeing MLE and regression using both of them. Okay. So for, let's say, if it's for this particular Gaussian related data, normal distribution, you say this distribution something like this, there is some ID and some X that is given. We see that, okay, it is normally distributed. Okay. Then if you plot your data something like this, what do you think if your data is mostly likely to be being generated from this A distribution, or is it distributed made from B distribution? So if you see, the data is entirely spanned towards the A distribution data. Now, hence we can say that it is more likely related to the A distribution. Now, since it is distributed towards A, it is centered towards A, it does not actually mean that it would not follow the B distribution. Like it might, we don't know which particular distribution has created which data. That's why we need to find the distribution, which exact distribution, we need to know that. Okay. So how do we do that? We'll first do nothing but we'll start by computing the likelihood for each observation. Likelihood is nothing but what? Likelihood is a maximum probability. So that is the height of the density function. And then we compute the Lth of I for every ith function. So likelihood for every observation. Okay. So this is how our likelihood contribution for the first observation came to be around this 1, 4, 5, 6. So it means that, okay, yes, essentially A was a distribution that was following a data set, right? Now what we do is, like, when we assume that the n number of intervals or variables are independently related, we take the product of all of them. So product of Li. In our example, it was 5 number of variables. You do it for 5 number of variables, right? You do it for 5 times. When you do it for 5 times by hand, yeah, you need a computer to solve it iteratively, right? So there is this two difference, not regression, I guess, the least square thing. So there are these two terms, or sorry, these two methods when it comes to solving a equation or a distribution, or when it comes to fitting your data with some particular model, when you want to see which particular distribution your data is actually following to. So you have least squares, where you minimize the error in between terms, or where you see the residual and you try to minimize them. Okay. And the other thing what you have is maximum likelihood estimation. So for least squares, what you do is, like, you just have your simple term or thing that y is equals to mx plus c. One is your slope, one is your intercept. For residuals, that would be your predicted value minus the observed value that you have. But there's one thing over here. When you get regression in this form, you also have an error related to it. Some bias is there. Now we say in these terms, the bias or the error is normally distributed. That we saw in the last class and during the week 7 lecture. That this will only work when the residuals are assumed to be normally distributed. That means in the QQ plot, all of your data would something like this only. It is a linear line or a straight line passing through origin, and that has an angle of 45 degree with the origin. So that is tan 45. That is 1. Okay. So that is nothing but in those cases only you'll be able to do least square. But with MLE, that is not the case. MLE is more general and you can apply it to n number of probability distribution function. It does not need a inherent definite condition that your error or your residual should only follow normal distribution. Okay, so that is the flexibility it gives it to you. Now we need to estimate some model using MLE. Let's say we have a term of error. It's not likely distributed, but let's say we made an assumption that it's normally distributed, mean is 0 and variance is sigma square. Okay. So we can write our error term as the observed value minus where it is leaking from. Okay, so observed value minus your actual predicted value. So this is something that follows normal distribution, mean is 0, variance is something like that. Likelihood for each density function would be like something like this. So we compute a distribution function for the second observation. So it's like you just input in some values there over here. You see those distributions multiply for all of the 5 values. Then again, you choose some values, do trial and error, and see which helps you to maximize. So then there is the sheet available in the important data files tab. So you directly read the particular folder. Then you do something as you import here. This is a new thing, that is you import minimize. So what will minimize help us to do? It will minimize the residual error and probability. So this is also second definition of maximum likelihood estimation. Okay. So what do I do? I'll just finally do is like, okay, X was my independent variable. Let's make a summary table for this. So I added X as a constant. I made a summary table for it. I got 0.98. I got this constant as negative. I got this X value as some intercept value over here. I see some probabilities over here. So for this, it is not. For this, it is. Something like those values. I just read it. So my B naught value is this and B1 value is this. So this is my B naught and B1. So my coefficient and the standard, the slope of it. Right, so this is my coefficient, this is my slope of the curve. Now I want to estimate the values using the MLE also. So this I only did using the regression analysis. What I'll do now, I'll find the residual. I take the residual. Now what I want the error term. So that's my standard error. So what I do is like, I'll find the standard deviation of the error term that I have, the NP dot standard deviation of the error. I got it like 0.0604. So I'll now compute it using MLE. So similarly for MLE, what do you want? We want this M and B, that is nothing but our regression coefficients. One is your slope, one is your intercept, another is your standard error. Standard error is not standard error, it's a standard deviation of the error term that you have. Now we need to compute or iterate it for n number of parameters, and then this L is your likelihood function. Where does that likelihood function come from? It comes from this thing here, this thing. Right, so you write it for one, you iterate it for the others. Yeah. You take the length of it, there's this log of 2 pi, then again you have a length by 2, then you have sigma square plus 1, you have 2 sigma square, you have sum of y minus yxp whole square. Okay, so in Python, you don't do this thing for squaring, you do double multiplication for squaring. Okay, you define your data set, it gives some independent and dependent variable that is from your this table only. If you think that I'm giving independently, so this is from my table only. Okay. So this is 14569, this is 267,915. So from the same table. Now what I'll do, I'll try to minimize it, my likelihood function, give some array. So this is some initial value that I'm predicting that my sample values would come to this value close, so that my function maximizes, my probability of the function becomes maximum. And this is using some n method. So there are different type of methods for optimization. For fitting, there's Nelder-Med, there's this McCord, something like those. So there are n number of methods for doing the same. Almost all of the functions would give you some, will give you same value or similar values, but there are only some specific functions which give you value in a way which are not actually, it's like, which have some inherent conditions and assumptions, so you can't do those directly. Why and how and which ones to do, the instructor will let us know in the further session. So that is how from that I'll be able to tell you that if we want to learn those or not, or else for now you just go through the ones that are there in the lecture slides and don't worry about the others, that why this is not being taken or not. In the assignment also, if something like this occurs, you also follow the same thing. Okay. Two minutes. Yeah, yes. So this is how we did. Now we find the likelihood function. So that was minimize of that particular function. So, okay, this is just solving the function. I didn't say anything about it. Likelihood of the function. Oh yeah, here. So these are your three values. 1 point. 2.82, 2.82, 1.33. So what are these? These are your regression coefficient, your slope, and sorry, your intercept, your slope, and your error term. Okay. So we'll do one such example and we'll try to quantify if the values that we are trying to get is essentially same to the values that we get in here or not. Okay. So this is not done in here. And what happened? Wait, I'll just see if we have those same values there. So this is a likelihood function that we get. This is the error. Uh, here. Sorry. So sorry. So this is your likelihood function. The likelihood function, these are your final values, not the below ones. Apologies for that. So this is the my final values. Right? So my So this is first one is my intercept, next one is my slope, next one is my standard error, standard deviation of the error. If you compute from here, this is your standard error, standard deviation of error, this is your standard deviation of error. So either way where you solve, your values would be same. So if you see, if you do it using either if you do it using the regression table, it would be similar. If you do it using this particular way, it will also be similar. But for this particular way, you need to know or you need to see the likelihood function. Now, if you don't know how to make a likelihood function, let's say these were smaller functions, so that's why you're able to make them. But if you don't know, there's a software called as Mathematica. So using this particular software, you can compute the likelihood function, you can do differentiation, derivatives. So this coding for this particular sample, you don't need any specific coding. It's just that you can take in your variables and then directly as like you can write it how you write equations. So there's no essential coding. It's like if you want to write a function, you write a function, then you give some colons, add a underscore. So all this you can see in it's in function manual. So it is similar to that, or by the after that everything's same. It's like you write your equations in a similar fashion. It just for that adding some power and all those do differ. For this it's like control, it's like control. Yeah, so for doing this particular this up arrow, that is a power one, you need to do something as control plus this 6 number key. So something like that. So there are some options as like how do you write. If you want to write a symbol there, so you'll have to do escape, and let's say I want to add a symbol something as infinity. I write escape and then colon, and then I'll write INF, and then the variable will give me something as infinity. So in that software there are some kind of it's like some norms that you need to follow, that's well of course, but with respect apart from that it's almost same. And then there you don't need to compute this likelihood function, so here you had to. But there's another alternative which is even easier. That is nothing but you do this regression statistics, you'll get the same thing that you have, right? So everything would be similar, you get this terms, and here from here you get the standard error. So this is like two-step thing. That is like one-step thing. But using the one-step thing, you need to involve your brain a lot there. So this is also good. Try doing this also, try doing that also, so that you are well versed with the two techniques that are available. Okay. Then there's same another example. We're doing the same thing over there, finding the residual, then you get the standard deviation of error. And then you do it using the similar thing, you get the values over here. Okay. So that's all for this session. All of the examples that we have and what we saw. We'll just do the previous year assignment questions and we'll be done. If you have any questions in theory, you can let me know now. We can take a 2 minutes break. If not, we can go ahead with the examples. Okay.
Do you have previous year question paper?
I don't have previous year question paper, but I do have previous year assignments. So that is how I can help you through them. Previous year question papers, you can perhaps try and ask in the discussion forum if they can give you for your solving or better, but it's like it's not shared with the TAs. So you can ask in the discussion forum if you want.
What is paper pattern?
Paper pattern is similar. So you'll get MCQs. Probably you might get some numerical or something where you need to write an answer to it, which are like, so in NPTEL exams, you don't have any negatives. It's only positive marking. It's no negative marking over here. You'll get MCQs. There might be some fill in the blank kind of questions, and can be similar to master following also. So similar to how JEE and all other exams have their own pattern. You will be given the calculator over there. And if some questions require you to solve extensively, there might be some Python snippets also. Python snippets as in you don't have to write the code, probably to interpret it. What it's trying to do is like, if I have to do something like this, how will I find? Let's say if you need to compute a mean, median, mode for something, which particular way or which particular snippet will you follow? So things like this would be there. And apart from them, something similar to your assignment questions. So how assignment questions are, exam questions would also be in the same fashion. Okay, any questions? I guess there are no such questions, then we can go ahead with the assignment hour and done for today. Okay, so I'll share my screen to do the assignment hour. Wait a second, what's happening here? Wait. Something. Yeah. So we didn't see the logistic regression part, but I hope you all might have done seen the slides, because there's only 2-3 questions there in your assignment, what I see for now from the second part. I guess I do have some questions on them also. So if if you haven't read it or went through the slides, it should be fine. But my advice would be go through that also. Okay, so here's the homework assignment questions. 2 minutes. There's something flying on my laptop. Okay. Here. Categorical variable. Wait. Where we want to see. Right. So for the first question, for this is our week 8. For the first question, for categorical data with n categories, the number of dummy variables would be
n-1.
Yeah, yes. In estimation of regression parameter, the likelihood function is a function of sigma, or is it a function of it's like the values should be such that they maximize the likelihood function? Yeah, yes, go ahead. So in the estimation of regression parameters, wait, okay, show again. Am I audible to all of you?
Yes, ma'am.
Yeah, it's fine. I guess I'm facing some network issues today. Yeah, so for the second question, in the estimation of regression parameter, which of the following would be correct? Screen is visible now. Yeah, yes, there it is. There we go. Yeah. So yes, we saw that the regression coefficients and the standard deviation should be such that it maximizes likelihood equations. That is what we do in regression parameters. Okay. Next question. Here, in logistic regression, the null hypothesis tested is what? We know that always a null hypothesis is what includes equality. Right? Now, if it includes equality, we know that either this would be an option or this would be an option. But what do we consider for regression? Do we consider a mean to be 0 or the regression coefficient to be 0? Yes, go ahead. Well, you all might know answer to this.
Mean to be 0.
No, because we aren't checking the mean of the population here, right? We are seeing if a regression coefficient, if it's either it's logistic or if it's our let's say linear regression, any such certain type of regression, we are seeing what that regression coefficient would come to. So we are taking our hypothesis based on it. We are not seeing the sample population or our population size or anything. So that is why we look at the regression coefficient to be at 0 first. Okay. Next thing in logistic regression. Yeah, so for now it's like from what all we started, this regressions what we saw previously was only for the continuous variables. From what we tried doing today is like we saw the MLE part, and then we also saw the categorical variables. What we saw is like there are things which depend on the category of a particular variable. So in logistic regression also, the dependent variable is categorical. Okay. So it depends. So if our population size or if our data analysis, if it's having some an effect based on some of the variables that are there in our entire data set. Okay. Then here, G statistic is used to check the individual significance of independent parameter. So there would be some another statistic that would be there in the further slides. We haven't went through it today. So this statistic, is it useful to check individual of another significant independent variables? Well, the answer is no. It's only for the dependent variables. We didn't do it. That's why I didn't ask the answer from you guys. So these were only two questions that probably we didn't do it, and those are there today. Now this is from simple maths. What's the range of the values as output of the sigmoid function? So if you want, I can also show you how a sigmoid function looks like. So, well, but for the sigmoid function to exist, what is the sigmoid function? It is 1 by 1 plus exponential of x minus x. Okay, so this is nothing but 1 by 1 plus e raised to minus x. Okay, so this is our sigmoid function. For any particular value of x, what the function would return you? Let's say my value of x is negative. What it will be return it to me? Will it have some negative values at any point? Come on, come on. Any hints? It's like if my function is something like this for the sigmoid function, would it return some negative values for any negative values? I think not, it will not. Yeah, yes, exactly. So for in negative values also, our function will only exist in between 0 to 1. So I'll share my screen and will share with all of you how it looks like. So yes, here, if you see, I just gave the range of it's like NumPy and Matplotlib. I defined the function of sigmoid function over here. Just gave some random values. Let's say for n number of 10 by negative 10 to 10, number of points in between them is 100, and made a sigmoid of x. So that sigmoid of x looks like something like this. So the values are only existing in between 0 to 1 for n number of data points that I have. Okay. The next question is, okay, there's some another question that is next. I need you guys to look at the question. So I'll share my screen again. Yes, now. So state true or false. The method of least square is used to predict the population parameters with any probability distribution. Screen is visible now. I'm not able to see share screen. Yeah, I guess now it's visible. Here. So the method of least square is used to predict the population parameters with any probability distribution. Is it true?
Yes.
Is it? So least square, we only try and see. We don't predict it through it. We see if we just do it for the sake of minimizing a data set. Later, something as regression does it. Okay. So that is the difference in
Yes,
between both of
yes.
systems. Yeah. So the least square is not used to predict the population parameters, where it is only helps us to minimize our differences in between the residuals or the errors that we have, and from them we let regression help us predict the population parameters. Okay, so this is false. Okay. Then suppose you have been given a fair coin, you want to find out the odds of getting heads. How many heads will you have? Which of the following is an option true for such case? So this is something to your what do you say, your categorical variable, something like that. So if you give some value to it, accordingly the terms to it would be. So if you say that you have a fair coin, will have some sides as head and tail, you want to find the odds of getting getting heads. So how it would be? Let's say if even got some 0, odds get some 1, so odds would be some 1. So this is would be true for n number of cases. If options as like all of the above, or just like, of course it won't be 0.5, but if options as me even also comes, odds also comes, so the option can be all of the above, something like that. Okay, so this is very is like a question which can be easily misinterpreted. Okay, so not that good question. Yeah. Then, large values of the log likelihood statistics will indicate what? So now here also, this type of question is also very something like which can be easily misunderstood, where large values of the log likelihood estimate statistics will indicate what? These larger values can be your R square value, can be your maximum value of the data set, can be your p value. So you have this number of values. Okay. Now the options are that there are greater number of explained and unexplained observations. No. That statistical model fits the data well. Can be if you assume that these larger values are the maximum values that you are getting through. Okay. That as the predicted variable increases, the likelihood of the outcome occurring decreases. Can be. We aren't predicting anything. We are just looking at the likelihood of the function. We are just maximizing the likelihood of the function. We aren't seeing if it decreases or increases. Can be. That the model is a poor fit for the data. So larger values can be that this p-value is higher in a way that it's more than 0.05. So it is a poor fit of the data. So your answers can be this also and this also. So do you guys have a take on it? That is how I feel that this particular question can be. Do you have any inputs to contribute for this particular question? Anyone? Well, okay. If someone has any doubt in it, you can stay back and let me know then. Next, there's a logit function or logit function, which they define it as L of x is a log of the odds function. Now, what could be the range of this logit function in the domain where it's only lying in between 0 and 1? Now, this logit function is similar to the sigmoid function. In a way, it is defined as log of x by 1 minus x. So where the sigmoid function returned you values in between 0 to 1, this function will map the opposite of it. So where for sigmoid, it was defined from all particular values, let's say from negative infinity to infinity, yet it returned the values in between 0 to 1, whereas the logit function is something that if it's in between 0 to 1, this because of this log, it will give you values in between negative infinity to infinity. Okay. So how does it look like? I'll share my screen and give you a live example of it. Okay. Yeah, yes, here. So if you see over here, this is how I define the logit function. I returned the value as log of x by 1 minus x, gave some values of the axis and just plotted it. So when I plot it, I see something like this. When I gave values in between all the terms, it's returning me values in between this negative and positive terms. Okay, so the output can be any. So it will return me the range of the logit function would be in the domain of, if it's in between 0 to 1, the output can be in between negative infinity to infinity. Okay, so it will map the values in between both of them. So do you have any questions? If you have, you can stay back and let me know, or else we are done for today. Thanks for joining. The last two questions were fine, right? You were able to understand those? Because I guess there are similar questions in your this year's assignment also. Yeah. So if you have any questions, you can stay back and let me know. If not, then we are done for today. Okay then, thanks for joining. We'll meet in the next session, next Tuesday.